Thank you for introduction, Tibia. So on a daily basis, I'm doing a lot of profiling and benchmarking stuff. And today I would like to share with you some of my knowledge and techniques that I gained during this time. So I will start first with saying a few words about what is special about the performance analysis that we do at Intel. Then I will kind of try to project it into how you can do this and how it will help you to analyze the performance of your application. And in the end, the second part, I will walk you through some of the dark corners of the performance analysis and possible pitfalls that you need to be aware of. So what is special about the performance analysis that we do at Intel? In the traditional software development, let's call it like this, we have our application, right? And hopefully we have some form of continuous integration, meaning that we have some nightly builds and unit tests running, and hopefully we also track the performance of our application. So for example, whenever someone will commit some badly performance code, next morning he or she will come to the office and will receive some notification say like, hey, the performance after your changes dropped I don't know, by X%, go please fix it. The important thing here is that the code of the benchmark of our application is constantly changing as we are changing our application, but we are not usually switching between different compiler versions, or maybe even compiler options are pretty stable, right? So, however, we at Intel, we have a little bit opposite reality. We have a fixed set of benchmarks that we are using to tracking the performance of the compilers. Meaning that each brand new day we will have a new compiler built from sources by our automated tracking system. And our automated tracking system will use this fresh new compiler to compile this set of benchmark, and then we'll run it. Okay? So the bottom line here is that the application developers are usually trying to improve their code, to change their code in order to improve the performance, but we will try to improve the compiler in order it will generate more optimal code, okay? So this picture also explains kind of a bit, for example, two different compiler versions, say yesterday and today, might generate completely different assembly that can result in some performance gap, right? So you can view it as, for example, yesterday and today, okay? So before I will go into the examples, let me say a few words about what tools do I use. It happens to be not that much. For profiling, I usually use perf. Well, if perf is not enough for me, I go into Intel Vitune. And good old bin details, right? So nothing prevents you from stopping the performance analysis right now, okay? And the second thing is, still surprises me, is how much people are not aware that they can improve the performance of their code just by using better compiler options. So you can just switch from 02 to 03 and have significant performance impact, but also they can use -march option. I know this option is probably is used a lot in the embedded stuff. We are always using it for cross compiling, right? But also,
what they will give us, those options?
Yeah. So the question was, what they will give us? Well, they will give us better performance. So,
no examples, please.
Okay, there will be examples after. Okay, yeah.
What do you prefer, compiling with the optimization way? So, with Visual Studio, you can optimize for smaller code or faster code. What do you prefer in this case?
Okay, so the question is, what do we prefer, optimizing for size or optimizing for speed? We do not care about the size so much. Yep, exactly.
It's faster and not if it's not.
So the comment was, so if I will try to optimize for speed, it will probably have better cache locality. Well, I guess O3 is kind of also like trying to address this. So usually O3 means like better than, for example, than OS in my experience.
Yeah, okay, but you can specify if you want to compile for fast or for the size of the code. So even if you specify O3.
Okay, okay. So there is a trade-off there. Okay, we're not focusing on the size of the binary. We're focusing on speed, like so crazy. Okay. So the second option, minus a march, it also tells the compiler, like, hey, Mr. Compiler, now you are able to generate the code for a particular architecture. Okay. So now the compiler will be able to fully leverage all the hardware capabilities. For example, vectorization, different instruction set. Okay. So here we have an example. So I compile and run the whole CoreMark ProSuite, and with -03 and minus a March Skylake, for Skylake platform, of course, it gives 9% better than O2. Okay, you might argue, well, not a huge performance win, right? But like we care even about 1%. Yeah.
Do you have any comparison to Haswell?
No. It's just to give you an idea, okay? So also this talk will not be about how to use like better algorithms. All the benchmarks that we use, they are already highly optimized, meaning that you will hardly find any performance, any major performance flaws inside, okay? So in this presentation, we will talk about from 5 to 15% difference, okay? Not the orders of magnitude. So this is the first case. So there was a performance regression one day. I will not name the compiler on which that happened, like specifically in order to not generate the bad impression about this compiler. Okay, so and like the execution times slowed down by 15%. So on the like some EMBC benchmark, it's actually an embedded benchmark. So what I did, so I compared, so I found, of course, so I profiled it and found the hottest place in this benchmark. It is really simple benchmark, so it has only one hotspot inside. So let's just jump into this. And it's so simple. It's just well, I stripped out all the code that is not needed, and it turns out to be like a simple for loop with a function call inside. Okay. So here's the assembly that was generated by two compiler by two compiler versions. Simply, so it was the same compiler but two different versions. You can view it like after and before. So and we have the performance regression. Okay. So by measurements, we know that this assembly code performs 15% worse than on the left side. Okay. So I hope that everybody familiar with X86 assembly, although you do not have to be, unless I will specifically walk you through the assembly like line by line. Okay. So what we can also see here that there is a backwards jump, okay, which essentially forms the loop. So okay, and we have the performance regression, minus 15%. Can anyone guess what might be the reason of this performance regression? Yes. Yeah, exactly. So so this is like the optimization that was that compiler did yesterday but failed to do so today. It's called loop unrolling. So basically we can see here that like in the code before, the compiler unrolled the loop by a factor of 2. So now we have 2 function calls in one iteration, right? But now we have only like one function call. So it basically now we are like forced to execute more jumps. To be precise, twice as much jumps as we did before, okay? So this jump instruction, decrement and jump. Makes sense? Does anybody understand why do we have twice as much jumps now, and why it is slow?
It's very expensive to jump.
Yeah, so I specifically actually point out, and I specifically renamed this function to small func, so that the overhead of those jumps is significant to the, in comparison with the amount of work that is done inside the small function. Okay? So actually, so this is kind of an easy case. I mean, it's an easy because it can be spotted just by looking with our eyes and compare the assembly, right? We will see immediately that the hot pass in our benchmark is different, okay? So the second case, again, in the real benchmark, now it's CoreMark Pro. Again, execution time slowed down by 10%. So in this benchmark, there are multiple hotspots. So I compared the assembly for all of them and found the one that was different. So let's go jump into this. So again, I'm not showing the source code because, well, it's not super relevant here. So essentially, we have, again, the loop with the backwards jump. And by measurements, we know that the right-hand side performs worse by 10%. Can anyone guess what might be the problem in this case? Vectorization. Yeah, exactly. So we can see that compiler yesterday generated the vector code with all the vector instructions, and it's now operating on the vector registers like XMM, YMM, and so on. But on the right-hand side, we can see like completely scalar code that's operating on scalar registers like ESI, RAX, RDX, and so on. Okay. Okay. So, this is kind of again those cases that you can understand what might be the difference, what might be the problem just by looking at the assembly. But what if you have the case where you like have two assemblies in front of you, you're looking at them, and you see that okay, they are different somewhat, but you kind of don't understand like what is what is so special about this difference. You want to know what is the higher level difference inside those assemblies, okay? And in order to have this information, the compiler have such functionality like compiler optimization reports. Like usually every decent compiler has this functionality. So imagine you have this full function. It's really simple. It's just iterating over an array of integers and just incrementing each element. So if you will pass, if you will add -rpass flag to the clang, it will emit you the text report saying like, okay, now we know that the first compiler unrolled our loop by a factor of 2, and then it performed vectorization on it. Okay. Well, so now we kind of know what to expect if we will look into the assembly. Okay. The great news is that now the same functionality is also integrated into the compiler explorer. So you can just hover your mouse over this over this green bar, and you will see basically the same output as before, but in the kind of a more human readable form. Okay. Okay. So now, how you can use those optimization reports? So imagine that you have this this loop, and well, okay, you emitted the compiler reports, and you can see that the loop was not vectorized. Well, because compiler decided that it was not beneficial to do so. Okay. But what if compiler was wrong? What if it is beneficial to vectorize this loop? So how you can test it? You can add this special pragma, like pragma clang loop vectorize enable. This pragma saying like, hey, compiler, if you are able to prove that it's legal to vectorize this code, just do it, okay? So now compiler will not look into its cost models and will not try to calculate the efficiency of the vectorized version versus the scalar version, and will just vectorize it. Okay, so let me kind of bring everything that we talked before together. So like how you can find optimization between these. So first, you measure the baseline. This is like the number one step that you should do. Second, you identify the hotspots. There is no need to optimize the cold path, right? And then you basically have like 3 options. So first, well, I think that it's good to see what compiler did for your hotspots, for your hot places. So it's kind of good to see what compiler did on a higher level. Maybe some important optimization is missing, or maybe something prevents to perform this optimization on particular piece of code. Okay. If that does not help, you can look at the generated assembly. So sometimes you might find some interesting things there. Like for example, you will notice that some particular instruction is like hotter than the others. So if that also does not give you any clue about what's going on, so you don't know how to like why it performs so badly, how to optimize it, you can collect the hardware events and performance counters. So what do I mean by hardware events? Well, hardware events is a branch miss prediction, is a L1 data cache miss, instruction retired. The performance counter, and I will actually have the example of how you can collect the performance counters. Okay. So now let me ask you a question. So does anyone had the situation in the past where you made some change in the code and you have no idea how it can affect the performance, okay? But for some reason it did. Okay, like most of the audience. So and one such example is like code placement or code alignment. So how hard do you think it is to measure the throughput of the function like this?
Depends.
Yeah, it depends. So, well, okay, it is a really simple function. It's just iterate over an array of integers like 32 elements inside, okay, and just increments each element. Well, okay, let's say we measured some number, okay, some number in gigabytes per second. So this is our throughput. But what if I will add exactly the same function right before the function that I want to benchmark? Will be any difference? There is no way how this full function can affect the performance, right? It's completely cold. No one is calling this function. But it just happens to be in the same source file, like right before our hot function, okay? So it turns out that the throughput is increased by 15%. Now, do not get me wrong. I'm not advocating for inserting like full functions right before your hot places, okay? Okay, so here are my measurements, okay? So and I can see, we can see that if I will add full, the throughput is just suddenly increased by 15%. So what I did, I collected this performance counter. It's called idq uops not delivered.core. And here is how you can collect it using perf. You just say perf start minus e, and then what goes after r is the hexadecimal code for this counter. I'm not showing specifically the numbers for this counter unless we will kind of try to understand what this counter means. Okay. So in order to understand what this counter means, I need to explain you a little bit of the X86 Architecture Details. So what happens when we fetch in our instructions from the memory? Well, we first feed it into the decoders. Decoders decodes our assembly into the sequence of so-called UOPs or micro ops. That is then feed into the rest of the pipeline. Okay. So and we have multiple execution units that do not execute your assembly instructions, but so-called UOPs or micro ops. Okay. And because we have multiple execution ports in the backend, we are capable of executing multiple UOPs in parallel, right? And what this counter means, it tries, okay, so, and for Skylake architecture, this number is 4, means that we can schedule 4 UOPs in one cycle, okay? And what this counter does is just counts how much slots that were available for scheduling UOPs were lost. So, for example, if we will be able, like, to issue 1 UOP in one cycle, this counter will be increased by 3. Why by 3? Because 4 is the optimal number of UOPs that we can issue at one cycle in Skylake, but we issued only 1. So there are 4 slots for issuing UOPs, but we just filled only 1 slot. Okay? So this counter will be increased by 3 in this case. If we will issue 2 UOPs, this counter will be increased by 2, right? 4 minus 2 is 2. So we filled only 2 slots of the 4 available. Okay? I try to explain as clear as I can. Well, it's not the super precise explanation of this counter, but I don't want to go too much into the details. Okay, so for this counter, the lower value means the better. Okay, so it kind of tried to approximate how good we are at fetching the instructions and feeding them into the backend. Kind of a high level. Okay. So here are the numbers for this counter. So well, okay. I can see that now we're doing much better. Or, okay, not much better, but somewhat better than before. This counter is like dropped significantly. So it kind of explains a little bit. So to make it even more fun, I did 2 more experiments. I aligned the function that I want to benchmark at the 32 bytes boundary. Like, don't worry if you don't understand this now. I will have like the example where I will like try to show you the code placement of this function in the memory. Okay. So I did 2 experiments. I aligned all the functions at the 32 bytes boundary, and I aligned all the basic blocks inside this function by 32 bytes. Okay. What is basic block? For those who don't know, basic block is just a sequence of assembly instruction with single entry and single exit. Okay. Loop essentially is a basic block. It has single entry, single exit. Okay. So you can see that the throughput is increased by plus 48% on Skylake. So like, what is the real number of the throughput for this function? Who knows, right? It depends how our function will be laid out in memory. Okay. Well, so okay, and here are the options that I used for Clang for doing these experiments. So now, okay, so now we know that the only moving part in this benchmark is the placement of our function. Nothing else is changing. Okay. So let's see how it laid out in memory. So I'm now showing you the code placement for those 2 experiments, for the last 2 experiments. Like, we'll try to compare them and try to reason about the performance. Okay. Okay. So this is the complete function sorry, this is the complete assembly for the function that we are benchmarking. Well, you don't need to look at the exact instructions. The important thing here is that the hot instructions that essentially forms the loop are highlighted in yellow. and let's say the cold are not highlighted. So this is the cache line in our instruction cache. Okay, 64 bytes, essentially like 4 rows. Okay, so what we can observe here. Okay, one important thing. Notice that compiler already aligned our loop at the 16 bytes boundary. This is kind of a default for LLVM. So LLVM kind of by default assumes that all the loops are hot, and it aligns those loops at least at 16 bytes boundary. So 16 bytes boundary meaning that if you have like 0 in the end, it's aligned at 16 bytes boundary. Okay, so it's like your address modulo 16. If it's 0, it's aligned. Okay, the same applies to, for example, what do I mean by the function is aligned at 32 bytes boundary? If I divide the beginning of the address of the beginning of the function by 32, if I will take the modulo of my address with 32, if it will be 0, it's aligned at 32 bytes boundary. Make sense? Okay, so and then we can see actually that now our hot code is split between 2 different cache lines.
But why first the cache lines are empty?
I'm just not showing the assembly. It's not relevant here. I mean, of course they are not empty, right? I'm just showing you like the code for only for this function, for the hot function. Okay, so and when I aligned all blocks inside the function by 32 bytes boundary, it happens that all my hot code goes down by 16 bytes. Okay, loop is the basic block. I align this basic block by 32 bytes, and essentially everything shifts by 16 bytes. So, and here is what I have. So notice the compiler inserted me a lot of knobs. Okay, so now my hot path resides in one cache line, in one instruction cache line, right? Yes.
Actually, I'm curious. So you introduced this new foo function, and did you use it somewhere? Because what I guess is that the linker will optimize it away.
Great question. Thank you. So the question is why this function was not eliminated from the final binary. Well, I just do not use LTO for specifically this case. So I do not use link time optimizations. The compiler cannot eliminate it. Okay, compiler like cannot assume that this function will not be used. Okay. Great question. Thanks. Any other questions so far? Yes.
Why a series of nops versus a short unconditional jump? In this second block, so couldn't you do a small relative jump and not force the compiler to run not?
Well, okay. So the question is, can we just change those series of knobs into like some kind of a jump here, like directly to there? Well, let me see. I have not tried it. But well, okay. So first observation. This knot happens to be like, let's count, 21 knobs. It's not like that. So we can actually we can encode like the big knobs with like 9 bytes. So and essentially, when we will fetch them, the decoder will just throw away those knobs. Okay. Well, this of course impacts our bandwidth, right? So it meaning that we are still like losing some bandwidth when we are like fetching the instructions will not be executed, right? Well, I think it might change something if we will like insert the jumps. Although I'm not sure if it will be faster, then we will just fetch knobs and just exactly at this moment throw them away. Okay, so the knobs are not executed; they are not fed into the rest of the pipeline. So basically, we are losing like only the bandwidth, the decoding bandwidth. Okay, makes sense? Any other questions? I hope it's a little bit not too confusing. So okay, so notice that now our hot path or our hot loop is fully resides in one cache line. Okay, so it meaning that we are now reading like twice as less cache lines. Okay, and usually it means better. Okay, so if you want to know more details about like how the hardware works in these cases, why it is exactly so, you can go read to my blog post. I wrote an article exactly about those 4 examples that I presented here, with much more details, with a little bit kind of my guess. How those instructions will be laid out through the pipeline and all those stuff. Also, there is a whole talk made by my colleague Zia Ansari on one of the LLVM developers meeting. This is the talk completely about the code placement and code alignment. So you might want to watch this as well. And also, finally, I want to mention this great paper that is called "Producing Ground Data Without Doing Anything Obviously Wrong." So this paper shows that if you will just even try to reorder the link, to change the link order of your object files inside your if you will try to change the order of how you are linking your objects, you might get like performance swings. And even in the way that O2 might be better than O3.
Kennen Sie eigentlich das Bochumer Institut für Technologie? Nein? Dann heißt es jetzt Ohrenspitzen. Denn wir machen Ihre Ideen zum Erfolg. Wie? Wir stellen Ihnen geeignete Forschungspartner aus Hochschulen und Universitäten zur Seite. Projektpläne, Förderprogramme, Antragstellung, auch das übernehmen wir. Lassen Sie sich diese Chance nicht entgehen und starten Sie mit uns durch.
So I have one more tricky case for you. Let me tell you a real story. So it happened like with me. One day I was analyzing one benchmark, and I spotted immediately the difference in assembly, like this, spread like through like all over the hot place. Okay, so like there were lots of difference like this. Okay, so what this does? So instruction in the left is like where basically reading so instruction on the left is read modifier write instruction. So it is Intel syntax. So Intel syntax means that the source is on the right, the destination is on the left. Okay, we're reading from the memory. We're incrementing the value from the memory and then writing it back. Okay, so the same sequence of instruction are written on the right, but kind of more explicit. Okay, so we are first loading from the memory into EDX, then we are incrementing the EDX, and then we are writing it back. Okay, and there was 5% performance gap. So what I also immediately spotted is that the number of instructions executed on the right-hand side was 50% more than the number of instructions executed on the left-hand side. So I decided, like, well, okay, I know what is the reason of the regression, right? Usually, executing more instructions mean more execution time, right? So I decided, okay, case solved, I'm good. And then I discussed this problem with one of my colleagues, and the day after I revisited this case again, and did more experiments on this. So I collected. So what I did, I put those instruction sequences into the tight loop. So I actually did this using a tool called URbench. It's available on the GitHub. Like, sorry for not having the link here. So what this tool allows you to do, it allows you to to write micro benchmarks in assembly and collect performance counters for tiny piece of assembly. Okay. So what I did, I put those two instruction sequences into the typed loop and executed 1,000 iterations, and collected those performance counters. So it's like instructions retired per iteration. Okay, per iteration. UOPs retired. So instructions retired means how many assembly instructions were retired. UOPs retired, it means that how many decoded instructions or micro ops were retired. And then finally we have the cycles per iteration. Okay, so if we look at the instructions retired, we will see that there is 1 for the fused case for the left and 3 for the unfused. Actually, it's no surprising, right? We have only 1 instruction on the left and 3 instructions on the right. Everything matches so far. But then we can see that the number of UOPs is the same. Okay? So what it means? It means that actually, so after decoding, there is basically the same amount of work that should be done by the backend for those 2 cases. Okay, and it actually explains why we have the same, why those 2 cases executed the same number of cycles per iteration. Make sense? More or less. Let's see.
What do you mean with cycles per iteration? Instruction cycles?
Well, it basically like counts how many cycles it took to execute 1 instruction. Yeah. So sorry. So okay. So the question is what do I mean by cycles per iteration? So it's how many cycles it takes to execute 1 iteration, and 1 iteration is those sequence of assembly instructions.
So instruction cycles, or clock cycles.
Yeah, clock cycles. So so you probably might have the question why it is 1 cycle. Do you? Because well, according like to instruction tables, for example, this assembly instruction has 6 cycles latency in Skylake processor, but it just happens to be like nicely pipelined. It meaning that for example, when we are starting like executing load from this assembly instruction, right on the next cycle we are starting execution of the load from the second iteration. Okay, so it gets nicely pipelined and like we are running super fast in 1 cycle per iteration. Makes sense? There are no dependencies. Well, okay, I'm not showing like the exactly memory address and stuff like this. There are no dependencies between iterations, so that we can like run super fast in 1 cycle per iteration. So what this case shows, actually like the performance of those instruction sequences is on par, means that it's the same, unless but there is an important thing here is like in equal conditions. It means that unless we were hit by some microarchitectural issue, like for example code alignment that we were discussing before, the performance of those 2 cases will be the same. So what it means, what I'm trying to say with this is that sometimes the number of executed instructions can be not the really good proxy for like making conclusions about your performance. Okay, so in this case I had 50% more instructions executed, but it was not the reason of the regression. The real reason of the regression was the code alignment. Okay, so like be aware about this. Okay, one thing I think I should say about is that there is definitely the difference in encoding. The case on the left takes 4 bytes to encode, and the sequence on the right takes 10 bytes. in encoding, and also the case on the right adds more register pressure to the compiler, because now it needs to came up with some temporary register, right? In this case, it happens to be EDX. So it's kind of not, there is a difference there as well. And I guess, like, my final note will be, like I encourage you to spend a little bit of time to getting more knowledge about how your hardware works. It will definitely pay off in your performance analysis work. Okay. If you're interested in those cases, I have them even more on my blog. Reach it out. You can reach me on Twitter. Okay. And with this, I'm ready for taking questions. Thank you. Yes. Okay, so the question is, if we are caring about, let's say, the code size more than about the performance, is it able to to go with some minimal alignment? Was it the question?
Yeah, so
okay.
so force it to not align anything.
To not align anything. Let me see. I'm not sure if you can override, let's say, default behavior, for example, of Clang compiler, because so Clang will always like try to align the loops in 16 bytes boundary. I'm not sure if it will like for example, if you will say minus m LLVM minus align all blocks, and for example say 0, probably it will like remove all the knobs before the loop. Probably. I actually haven't checked that, but it might be the case, yeah. Any other questions? Yes. Okay, so the question is, like, if you are working on some operating system, there are some kernel modules special for like collecting performance counters and like all this stuff. Is it able to have the same on bare metal? So I'm actually not sure. I haven't ever tried this. I'm like usually working like on some operating system, but I think that everything kind of boils down to some particular instructions that you can like, so you can decorate your assembly with those instructions. For example, like for X86, like there are particular instructions that like saying, hey, like I'm starting the measurements here, I'm finishing the measurements there. So there are hardware instructions. I think that like your architecture might have something similar, but I'm not sure if there are any tools for bare metal. Probably you will be forced to go into some assembly. Okay, so the observation was that there are some special like intrinsic for this, right?
Depends.
So I'm not sure that I understand you correctly. So so you're suggesting like to move your hot function like into another one, like.
So if you have your hot if you have a, let's say, a somewhat larger function,
Okay.
and some block of it is a hot
Okay.
block, that will not get aligned maybe by the compiler. But if you move it in a separate function, it might get aligned because of the default alignment that functions get.
Okay. So so the comment was, like, if you have a really big function and like some particular hot loop somewhere in the middle, and there are like a lot of stuff before and a lot of stuff after. So like how you can be sure that you will have, let's say, reasonable performance. Reasonable code placement of your hot pass.
Yeah.
So and your suggestion is like you can move it from another function, like extract this hot pass.
Maybe the assumption would be to not use them.
So okay, so well, first of all, I think we should also like consider like the compiler will like usually aggressively align, inline this function, like unless you will you will tell it not to do so. But usually, like in my experience, it's really hard to predict. It's really hard, like, to predict what will be the best alignment for your code placement, for the placement of your hot pass, like, because it's like so many hardware features inside the CPU that you need to satisfy. Okay. Yeah, and so even so, answering actually like original question. So even if you will extract this hot pass into like some separate function, it still will not like give you any kind of any kind of insurance. You cannot be sure that it will be properly aligned still. Yes. Yeah, great questions. Thank you. So the first question is, like, does the alignment issue goes away when I use link time optimization? And the answer is no. So because, like, well, actually, like, so the code alignment, the link time optimization may eliminate those functions that are not used. But let's say if I will place some call to this function, that will still be called. Well, the problem will not go away. Okay. And the second part was if I have like a really big project and I have multiple hotspots inside, can I be somehow like what is the impact of the code alignment in such case? And I can say that usually those problems like go away with the number of our hotspots increased. It means that because, well, it's not likely that all our hot places will fall down, will end up with the bad alignment, right? It's just not likely to happen.
Just bad luck.
Just bad luck, yeah. Yeah. So actually, so one more comment. So we at Intel, we tried to come up with some kind of a strategy how we can deal with those kind of things. We really tried different options. We tried, like, we measured a lot with different alignments, but nothing really works out. So if you fix one benchmark, but the other goes down, okay? So it's not like there is no silver bullet for this. At least we do not know this yet. Yeah, I think well, actually, okay. So the question is, I do care about the code size. I do not care about the performance much. I care more. Okay, I care more about the code size, and I care a little bit about performance. So should I use O2 instead of O3? Yeah, I think so. Actually, O2 is reasonable. So as far as I know, O2 is the most popular optimization flag in the world. Like, yeah, that's actually true. Like, it's most popular.
O3, that's what I want to know about O3.
Yeah. I mean, so like, if you really like want to squeeze out the final bit of the performance from your application, like, go for O3. Well, O3 will also, of course, will result in bigger compile time. I'm not sure about the code size. It's kind of a, I think.
O3 likes to do a lot of vectorization.
And unrolling as well.
Make big instructions.
Right. Yeah. So the comment was O3 like usually goes further in loop unrolling and vectorization stuff, which usually results in more code size. However, I think there are more cases when with O3 the code size can be still smaller than with O2. I think there are some cases. Thank you.